All right. Hi. I hope you can hear me. So we'll start. I guess it's already time. I'm not sure if people have any specific questions with regards to what we did, last week. Could you just confirm if you can hear me?
Yes, sir.
Okay. All right. Great.
Yes, sir.
All right. All right. So what I'm going to do is I'm just going to share my screen and then we can start.
Sir,
Yes, sir.
you did not, the last meeting's recording, you did not post yet on the Moodle.
Oh, yes. I haven't rendered
You
them yet. It's a lot
said
of work.
by Saturday.
Yeah, I haven't rendered those things yet.
Oh, right.
But I have uploaded the notes. So the slides are already on the Moodle. As soon as they're done rendering, I will upload them. They're not rendered yet. Okay. So we continue our conversation from last week. If there are no questions, here's to hoping you can see my screen. Right, so we started off our discussion of so-called primary memory by initially discussing CPU cache, so-called CPU cache, and we did make mention of the fact that we skimmed through registers because we already had a dedicated discussion of registers, or at least we already had a discussion of registers when we looked at the CPU, and it turns out that this discussion around registers manifests itself once we start looking at the computer architecture component of the course, because in fact, when we start looking at the instruction set architecture, and specifically MIPS assembler and the so-called MIPS data path, what you notice is that we'll be making reference to a lot of additional registers, right? So not just the special purpose registers that we highlighted, but integer registers. And although we don't discuss this, but typically your CPU have floating point registers and integer registers. Doesn't matter which one we focus on. We tend to focus on the integer registers. So that discussion is coming back. And then we also kept on making reference to the so-called memory hierarchy, right? Which explicitly or visually shows us the behavior of these different memory components. Behavior in terms of their capacity or their size, their behavior in terms of what happens to the data when there's electricity being supplied to the memory component. And also, more important thing, I guess, for most people is this whole notion of cost. What we've realized is that there's interesting behavior associated with these aspects here as you're moving away or towards the CPU. The behavior of some of these memory components is a bit intuitive here, right? So for a component to be located on the CPU means that it has to be significantly smaller than a component that is not located on the CPU, for instance. Certain things are not that intuitive. Like if you start looking at things like throughput, for instance, it turns out that the fundamental difference between a component that you typically find on the CPU in terms of throughput is usually associated with the technology used to implement it. Remember, during our discussion of primary memory, we keep on mentioning or keep making reference for the vast majority of the time is notion of RAM. We discovered that typically components that are on the CPU are manufactured, or they fall under the category of so-called SRAM, right, which is relatively faster, more expensive also, right? More expensive because you tend to have more transistors on the component itself. All right, so this diagram is still going to come up until we are done with our discussion of memory, and you see it manifests itself actually once we start looking at secondary storage also. So the next component we're looking at, and you remember, note here that we are moving down, we are moving away from the CPU, right? So the CPU registers, cache, various types of cache, level 1, level 2, level 3 cache, then we now zero down to so-called RAM and ROM anyway. So we're saying here that, I don't know if this statement makes sense here, but I think that RAM is the most widely used memory component. I hope you get the picture though. I mean, I guess it's a most commonly known type of primary memory, right? The statement is a bit, it's a bit confusing if we say it's most widely used here, right? But anyways, it's a temporary storage location, right? Meaning that it's volatile for the most part. It's volatile. As soon as you stop supplying power to it, you lose the data, right? If you are working on your computer and there's no power, right? There's load shedding or something, you run out of auxiliary battery power on your laptop, and your computer shuts down, you lose everything, right? Gone, because there's no longer power being supplied to the RAM, right? Similar to registers and cache, it's a temporal storage location for program instructions and data. But in this case, if we're to draw comparisons between registers and cache, what we are storing really is significantly more program instructions and data than we would store on registers and CPU cache. And this makes sense. It makes sense because RAM is ideally a staging area. So every time you execute a program, that program or the instructions that are associated with that program, at least part of the instructions associated with that program, will be loaded into RAM, right? And it's from RAM that the CPU will start its fetch, decode, execute, store cycle, right? So fetching individual instructions associated with that particular program that's loaded into RAM, right? So the difference here in terms of, in as much as we are storing data and instructions on registers and in cache here, the fundamental difference is in how much of the quantity we can store. And we can see this. We can see this from the capacity, right? If we compare the capacity of various levels of cache, this is my computer, and we do the same thing for the capacity of how much RAM I have, you notice that I have, or at least this computer here, has significantly more. If we can draw comparisons here, if people want to do this, it'd be nice to do some calculations so that people understand this. Observe, assuming we say the total amount of cache we have, right? Level 1, level 2, and level 3 cache. Let's just assume that we have, and this is just a rough calculation here, but let's just use level 3 cache. You're saying that we have the uppercase K here, right? We have 8,192 kilobytes of level 3 cache, and we have, just with the flow here, we have a total of 11 GB of level of RAM, right? You notice that about converting this to megabytes should be times that, converting megabytes to kilobytes should be that, right? So in fact, what we have is we have 11,534,336 kilobytes of RAM, right? And we can see that our RAM is literally, it's literally orders of magnitude higher, right, in terms of capacity. So my computer currently has 1,408 more capacity. My RAM has this much more capacity when compared with level 3 cache. Right? So this helps exemplify how much of program instructions and data we can actually load into RAM when we compare RAM with cache, with CPU cache. And it gets even better as you're going high up the hierarchy. Level 2 cache significantly smaller. Even worse still when you start looking at level 1 cache, right? So this would be like the cache that resides on the individual CPU cores. Right? I don't understand why people, this is the last time I'm admitting people like this. Why can't you just log in with your own email accounts? It's irritating, I tell you. People just never listen. Very sad. So in terms of where RAM is typically located, right? So this is not always the case. It depends on the form factor of the device, obviously. The location of RAM is obviously different when you're making reference to a tablet or a smartphone, for instance. But typically, if you're making reference to a laptop or a desktop computer, RAM is typically stored somewhere on the motherboard in what are called DIMMs, right? So these components that are called, or slots that are called dual inline memory modules, right? Module slots. So the RAM chips themselves are what are called DIMMs, right? And I think there's a diagram here that showcases that. And then you just plug them into the motherboard. Things are somewhat changing, but on average, you typically have maybe 2 to 4 slots, depending on the sheer size of the computer system that you're making reference to. For instance, if you're looking at a server computer system, what you immediately realize is that the form factors, if you were to compare it with a microcomputer, it's ideally, for the most part, significantly larger in size, meaning that you can fit a lot more components on it. So you typically have additional slots in the server computer system, right, when compared with a microcomputer. But the typical microcomputer will have maybe 2 to 4 slots where you just slot in these dual inline memory modules. And they come in various sizes. Hello, is there a question?
Yes. Does that mean that the larger the physical, the tangible component of a computer system, the more RAM it has? It has more RAM because it's big. Because you said it's because it's big. A server computer is big, so it has more RAM.
Not quite. No. It means it has the ability to be slotted in with more RAM, not that it has more RAM.
Oh, right.
It's possible that you might, yeah. So it's just the ability, right? You see, you have to think about this from the perspective of size. You look at your laptop, right? Or you look at your typical desktop computer. You look at the size itself. There's additional things that you need to slot onto the motherboard, right? So the larger that thing that you have, the more capacity you have for you to slot in these various components. Like for instance, I don't know if this is still the case, but it used to be the case at least a few years ago. Last time I checked, I haven't gone shopping for a desktop computer in a long time here. But typically, a desktop computer will have these hollow slots, which are called expansion slots, right? And the idea behind that is because you don't have expansion slots on your laptop, but the idea behind expansion slots on a desktop computer is that it has a significantly larger form factor, making it possible for you to enhance its capabilities by plugging in additional device drivers, right? Or cards, so memory cards, graphics cards, and whatnot. Not the case for smartphones, I guess. So this is what you typically see, right? On the motherboard itself, heatsink there. So these are the slots we're talking about, right? You notice that this particular image here has 4 slots, right? So meaning that you can slot in a total of 4 DIMMs here. Now the idea behind the DIMMs is they come in different sizes. So it's entirely possible that maybe when you purchase a brand new computer, it might come with these DIMMs that maybe have a capacity of about 2 GB, right? In which case you have a total of about 8 GB. But what you can do is you can swap them out for a higher capacity DIMM so that you have more RAM. Right? So it might not be possible for you to if you have a total of 8 here, 2, 2, 2, 2, it's not possible for you to add on an additional DIMM module, but what you can do is you can replace a lower capacity DIMM with a higher capacity DIMM. Right? Incidentally, I did this, is it last year or before last year or something, when I was purchasing my IdeaPad. The IdeaPad itself doesn't come with 12 GB of RAM, right? It comes with, at least the one I got came with, I think it was 6 GB, it must have been. So I spent a bit extra money to get high capacity DIMMs. And because I had nothing to do with the ones I swapped them out, I just sold it back to the company, or to the company that I bought it from. Right. All right.
Dr. Lighton, just on the part where we're also talking about the slots and the maximum capacity of RAM.
Yes.
What's the possible explanation where a computer, since even if it has got like 2 slots where you can add your RAM, but the manufacturer indicates to say the maximum capacity this computer might hold, maybe it's 8 gigs of RAM, and you had this idea to say I'll buy 2 8 gigs of RAM, and then on those 2 slots I will add them both and then maybe get a 16 gigs, but the manufacturer indicates to say no, the maximum it can support is 8 gigs of RAM, even though you have that chance of expanding the idea of having more RAM on your machine. Why would
I
that?
had no idea. This is the first time I'm hearing about that. I mean, I had no idea there was it could be a limit. I don't know. Last time I checked, there was no limit onto how much RAM you can plug into your machine. But if that's the case, it would be nice if you would share on the mailing list where exactly you found this information. Like an example of a computer system that you've come across that has a limitation on how much RAM you can add. Are you able to do that?
Yeah, oh yes, I'll do that. I'll do that.
Yeah. So I don't know an explanation. There is obviously an explanation, I'm sure, if that's true. But yeah. Right. So I mean, this is we keep repeating ourselves here, and we'll continue repeating ourselves until we're done discussing primary memory. Right. RAM, like most primary memory components, require constant supply of electricity. Right. So that the data remains persistent on the memory component itself. Right, and we've already made mention of the fact that typically there's 2 classes of RAM, so-called dynamic RAM and SRAM. The fundamental difference is in the price, right? So SRAM is typically more expensive than dynamic RAM, right? Again, this has become second nature, just to emphasize the fact that the role of RAM is to act as a storage or as a staging area for programs that the computer system needs to execute, or programs that the CPU needs to execute, right? So every time you execute a program, the first thing that happens is the instructions, or the program instructions, or portions of the program instructions are loaded into RAM. And then the CPU will start executing the individual instructions associated with that particular program. And at this stage, hopefully you've started painting this picture of what typically happens to the instructions from the time they are staged into RAM or ROM, right? Individual instructions and data are fetched one at a time. They'll probably find their way, they'll find their way passing through cache there, right? Find their way to the registers where all those fancy things we talked about begin happening, right? So the program counter starts doing its thing, the memory address registers and the buffer registers start doing their magic, right? And then as you continuously execute the instructions associated with that particular piece of software, some of the instructions, the ones that are commonly being used, are being cached into CPU cache, so that the CPU does not have to waste time making the round trip to RAM to go and fetch the instructions. So instead, they'll be fetched from the cache itself. Right, and so this idea of RAM being unable to hold significant amounts of data and instructions will manifest itself once we discuss virtual memory. So just trying to put it out there that there are instances where you might not have enough RAM, enough capacity to hold whatever program instructions you have running. And it's become common now where you have people running memory-intensive applications, and where still they multitask, right? I do that a lot myself. This is probably best case scenario. I'll typically have a slew of applications open at the same time. And so if it so happens that the amount of RAM capacity that I have is not sufficient to hold the program instructions that I'm executing, remember, it's not like I'm executing them at the same time, right? But if it so happens that there's insufficient RAM, part of the program instructions can remain on disk, on so-called virtual memory. They will be fetched from there. But also, besides the idea of virtual memory here is, you have to think about this from the perspective of what typically happens in operating system, right? We said that only portions of the operating system are actually loaded into RAM. The remaining program instructions are stored on disk, right? And they are fetched from disk, loaded into RAM as and when required, essentially. So just an example here, just to try and tie some of these ideas we've discussed in the past. A common utility software tool that you find on a Unix-like operating system is a software program called free, right? So free takes in a number of arguments here. Notice I'm feeding it an argument of h here, the flag h, and what it does is it presents, it gives me an idea of how much memory I have, how much of that memory is currently being used, and how much free memory I have, right? There are a number of other utility software tools that are available out there, right? So if you still have a VirtualBox, if you still have a virtual appliance installed, the one that you set up as part of one of the labs that we had, I do encourage you to play around with some of these utility software tools, so that you have an appreciation of how you get to gain a sense of how much capacity you have, right? So another utility software tool you can play around with is top, right? I'm sure there are a number of flags you can feed this to visualize memory usage in a more human readable format, right? This is in kilobytes. You notice it's not very intuitive, but you know, if you divide this by 1024, you should be able to get something close to 12 GB of RAM. Right? And the screenshot, by the way, is for another computer that I have, which has slightly less RAM, right? So it has a total of about 4 GB, right? The one I'm using right now has about 12 GB. And again, I mean, just to pause a little and talk about some of these utility software tools, it's rarely the case that a normal user will tend to use these utility software tools, and it makes sense. It makes sense because we said that some of the reasons why we tend to use utility software tools is to try and monitor and manage our computer system, right? A normal user would rarely have to worry about monitoring a computer system, for instance. But if you're a system administrator and your task is to oversee important server computer systems that house applications, maybe banking applications that are required to be available 24/7, these become extremely important utility software tools that you need to interact with. Yeah, user calls in, your system is too slow, right? What do? You start checking computing resources. So I was just introducing top here. There are a number of utility software tools. Some of them, so tools like top and free, for instance, will typically come bundled with your operating system. And I guess we can check for more. Some tools that I haven't even used myself. But the additional third-party tools that you can pull out, that you can download and install on your computer system, right? If you feel like these utility software tools that come bundled with, there's free here, that come bundled with your operating system are not good enough, right? Most third-party applications, its major selling point would be that they have a graphical user interface that is more visually appealing, right? So something that is a bit intuitive. But remember again that if you're faced with a situation where you're overseeing several computer systems, the interaction with the several computer systems will be remote, right? You will not have a GUI, a graphical user interface, which is why sometimes it pays to actually get to learn how to use the command line, I guess. I hope this is making sense. Again, just to pause for it. Is this making sense? I don't know if I'm still on there.
Yes.
Okay, right. Thanks for the acknowledgement. Again, just to wrap it in, we're still looking at the top part, the part where you need to have a constant supply of power for the most part. Electricity has to be constantly supplied to the memory component. Again, the comparison can easily be viewed from the perspective of these different aspects that we spoke about here. By the way, this throughput here, throughput is the same, speed, efficiency, one and the same thing, right? Is that a question? I see someone has a microphone on. Okay, could you just switch off your microphone wherever you are then? Somebody has their microphone. Thank you. Right, so a variation from RAM here is a so-called read-only memory, right? We could loosely say it's non-volatile for the most part, right? And so you typically have ROM being used in embedded systems for the most part, or components where you have program instructions that will rarely change, that won't change or rarely change, right? So all you're doing for the most part is just reading information from that memory component. And it makes sense for embedded systems. Why? Because these are typically, for the most part, these are single function devices that will not do any sort of processing. Well, there is some processing that takes place, but there isn't really that hard requirement for data to be written back to the component, like the BIOS, for instance. What it does is it expects you to provide it with input, right? And then based on what sort of input you provide it, it gives you back an output. There's no storage whatsoever, right? You're not writing anything to that component. Things like embedded systems like that ZESCO customer interface unit that I hope I brought it in one of the sessions we had, the face-to-face sessions. All you do is you use it to interact with, I guess, the main system at ZESCO, right? So you punch in some unit that you get after you buy, you buy power or something, and then it acts as a third-party entity that interacts with the main system to verify that the code that you've punched in hasn't been used, that it's valid. And then if you're successful, then your account is credited with the units, right? No storage of data whatsoever, right? So read-only memory. Now we are saying it's read-only. It's read-only, yes, but it turns out that there are certain variations of so-called ROM that can be, or that allow you to, that enable you to change whatever program instructions or data are stored on that particular memory component, right? So besides ROM, which is obviously the manufacturer, we embed program instructions on ROM, and there's really no facility or ability for an end user to be able to change that, but there's a variation, right? So you have so-called programmable ROM, right? Which erasable programmable ROM, which allows you to reprogram the memory component. So you can, it's possible for you to change the program instructions, right? Most modern day computer systems will typically be accompanied with erasable programmable ROM, right? Making it possible for you to be able to update the BIOS, for instance. Remember, when you're updating the BIOS, what you're doing is you're changing the program instructions that are on that particular memory component, meaning that it's technically not not read-only per se, right? So you can change the contents of the memory component. Just to try and wrap it in here, this came up last time we had this interaction. Somebody was gave away the answer when we asked how it's possible that the contents of ROM or EEPROM persist, right? Once you stop supplying power, right? There's a battery. So this image is just showing you location of the CMOS battery for this particular motherboard. Right, so a visual representation of the different classes of what we might call primary memory, right? So RAM, ROM, right? This is a sort of hierarchy that you have. Under RAM, you have SRAM and DRAM. Then ROM has different variations. So you have programmable ROM and erasable programmable ROM as well. All right, and then, right, down the hierarchy of so-called primary memory is this component we are calling virtual memory, component that's called virtual memory. And it's called virtual because it, technically speaking, doesn't exist, right? It's just a cheap trick that's used to fool the computer into thinking that it has slightly more RAM than it technically has. And so the idea behind this is if you have enough secondary storage, which is almost always the case, because it's much cheaper, you can buy a lot more of it. So if you have a lot more storage space, what you can do is you can format part of it and convert it into virtual memory, right? So that if you are faced with a situation where you're running a memory-intensive program, or you're running a number of programs and you don't have enough RAM, for instance, part of that hard disk that has been converted into virtual memory will be used as RAM, right? But the drawback with this is that obviously access to the program instructions is going to be much slower because secondary storage is for the most part slower than RAM because of the technology, right? And you look at this once we start looking at secondary storage here. So your average secondary storage medium is usually, not always, but it's usually it usually falls under the class of so-called magnetic storage, right? And I think you've noticed this in computers where if you're accessing something, you hear a clacking sound, right? It turns out that the clacking sound is there because access to data is sequential, right? So there's no random access to data. Because access to data is not random, it's much slower because every time you try and access data, what's the component again? The hardware has to, is it the spindle? I've forgotten the component, but it has to be moved to the location where that particular data is located, right? Drastically reducing the amount of time it takes for you to gain access to the data that you want, right? So making it slower.
Sir.
Yes, sir.
What if it was in the case of a solid state, is it solid state device, but the SSD storage unit?
Yeah, I mean, so that's an alternative, but still, the speed at which SSD drives, well, some of them, I guess, these days maybe operate at more or less the same speed as RAM. That's a different case altogether. So you'd probably get away with that. So if your secondary storage medium is, I guess, it's an solid state drive, then or solid state disk, then that argument of it being slower sort of like fades away, right? And we've seen this happen, I guess. I don't know if people have noticed this, but if you have a computer that has a solid state disk, right, as opposed to magnetic disk, for instance, what will happen is you probably have noticed that there's the loading, right? The operating system, the process it takes for once you switch on the machine, the operating system is bootstrapped at a much faster rate than magnetic drive, right? So yes, to answer your question, if you're dealing with solid state disk or drive here, it changes, right? Because access to data is actually random, it's not sequential. And by the way, during our discussion of secondary storage, we look at these different technologies that are used to manufacture secondary storage. So we'll be able to discuss that, right? But here's another thing to think about, right? In as much as you can do all of these things, you should not forget that cost is a very important aspect. If you have a computer, you buy a computer and it has a magnetic disk, a magnetic drive, and you want to swap it out for an SSD drive, you'd have to spend additional money for that. Where still, the lifespan of an SSD is much lower, right, than magnetic tape. So those are things to think about. I foolishly swapped out, on my current machine, I swapped out the magnetic drive that was, or disk that was in my laptop with an SSD, right? And it makes my machine somewhat faster, I guess, which works. But I know that it's not reliable when it comes to consistent storage of data, which is why I rarely store the things that I have on this machine. I rarely store them on my SSD anyway.
Now, sir, it being an SSD since it doesn't have moving parts, isn't it supposed to last longer than the HDD itself, or HDD? Sorry, hard drive disk. Considering the hard drive disk has moving parts and it can just easily stop working at any given time.
Well, I mean, so you're looking at it from, and I know where this is. I know where this is coming from, right? Is it the mechanical components, wear and tear, and well, yeah. I'm trying to see if I can think of an explanation for. So your argument here becomes flawed here, because what you don't, in as much as there's a lot of wear and tear, right, because of removing parts in magnetic storage device like your hard disk that comes with your computer. But the thing here is that there's a difference between the drive itself and the disk, right? So the thing that might end up rendering your magnetic drive useless is the drive itself, not the disk. So you can easily swap out the disk for another drive, right? Understand that? Anyway, so it turns out the lifespan of SSD is much lower because of the random access to the data on the memory component itself. All right. So again, this is back. Now, when you're checking these things on Windows, I don't think that you'd see virtual memory in terms of like swap space and whatnot. It probably comes with the different name. I don't know if it's paging memory. I don't know if they call it, they still call it paging memory or something. So you have to create page files. It's a complicated process. Last time I did it, it was complicated many years ago. I don't know if they've simplified this. I guess the reason why it is complex is it's supposed to be done by someone who has a bit of experience doing this. All right. Okay, so back to our memory hierarchy, right? Again, the top part, power is important. It's obviously costly, which is why your typical computer system is normally associated with very little of it, right? Unless if you're dealing with a very important computer system like a server computer, which you know will be able to make you more money, right? But otherwise, if it's a normal microcomputer, you know, what you typically have is a situation where you have far much less RAM in comparison to secondary storage, for instance, far less CPU cache in comparison to of your secondary storage in comparison to RAM. So far less level 1 cache in comparison to level 3 cache, for instance. Right. I have no idea how much thumb drives cost now, but it's become so cheap now. So mass production of content. Okay. Again, in terms of memory hierarchy, let's always remember that these different memory components are best understood from the perspective of these three key aspects, right? So the capacity of the component, its throughput, speed or efficiency is one and the same thing, and the relative cost, right? And the behavior is almost always such that as you are moving closer to the CPU, you tend to spend more money. The components are much faster. They are also much smaller, right? They are much faster because you want them to operate at least at the same speed as the CPU or at a speed that is as close as possible with the CPU. All right, again, our so-called memory hierarchy here is coming back, the pyramid. In terms of volatility here, I guess this table just shows us the behavior of the different memory components. Most all of them are volatile, with the exception in quotes of ROM, right? Another way of looking at the difference here is in the quantity of program instructions and data that are stored on these memory components. All right, so I don't know if people have any random questions here. I was looking at the syllabus and we're somewhat behind time here. I hope we'll be able to catch up. In the past, we would have covered everything up to secondary storage in the first term. So any random thoughts about this? Questions, concerns? Is this helping you understand the abstraction? So is this any better in helping you understand what we had previously abstracted? When we initially started talking about the polynomial architecture, there was, we just mentioned that, there's this idea of the stored program concept where both, and this is a key one, both data and instructions are stored in the same location, but we now see that this so-called same location manifests itself in so many different forms. If you think about it, all of these things we are talking about here, right? All these different memory components we are talking about here, there is data and instructions being stored in these things. Both data and instructions are stored in the same location. In fact, even on secondary storage, when you install a piece of software, I just installed, I've downloaded an illegal copy of Leagues of Legends or something, whatever, and I've installed it on my computer, right? When you're not executing it, the program instructions, the corresponding data, obviously, are going to be stored on memory, right? Secondary storage. Once you execute that piece of program, portions or all of it, if you have enough RAM, or depending on the size of the program, will be loaded into main memory. From main memory, as the CPU is executing that program, individual instructions are going to be pulled from main memory, taken to the CPU into the registers. In all these different instances, data and instructions, data and instructions. And we saw this when we were simulating the fetch, decode, execute cycle. Although, I mean, we abstracted a lot of things there, but we noticed as we were walking through some of the instructions that if you look at the MBR, for instance, in certain instances, you'd have the instruction, both instructions and data being stored in the same location. Excuse me. I hope this was clear. If there are no questions, I'm going to rush for another class.
Sir,
But if yes,
just before you go, I'm not sure if I did get it clear, but what would be the disadvantages of virtual memory?
it's slow. That's a major disadvantage. It's slow. So here's the thing, right? That's actually a good question. Here's the thing. There's nothing stopping you if you're like Lighton and you have. By the way, I did this a lot. We did this a lot when we were students. I remember when I was in second year when I first went to the computer science department, right? Second year, we were working on these machines that had what? Is it 250? Could you switch off your microphone? 250 megabytes of RAM, right? That was, and at the time there were exciting applications that we wanted to interact with. We used to download a lot of illegal games, right? You know, when you're young and dumb, you're carefree and you download illegal copies, you know, cracked versions of games. For us to be able to run those games, we had to create more virtual memory. But the thing is, your application is extremely slow, right? It's not even, I mean, the usability, right? It's not even, the usability of you interacting with that software is actually compromised, right? Because, you know, imagine a situation where like you're jumping, right? This game character, and you're jumping, and it's so slow, right? So this major disadvantage is it's slow. You want RAM to be fast, but if you use virtual memory, it becomes so slow. That would be the disadvantage. Any other bright comments besides that? Okay. Yeah, I think in the next session we start looking at I think is it file systems or something before we set the stage for a discussion of secondary storage, because it turns out that secondary storage is primarily there to persistently store data, right? So before we can have a discussion of secondary storage, we want to have a thorough understanding of how this data is organized. It turns out that there's a logical way in which data is stored on persistent storage, right? So files and folders, file systems, that's what we're discussing next. Guys, I will see if I can. I don't think I have class tomorrow, but I will upload these things tomorrow. Don't have class tomorrow. I'll upload these things tomorrow, all of them, the videos, so that you have access to them. I do apologize, it's been a hectic schedule. I wish there was a tutor for this course, right? Because then the tutor would be responsible for uploading the videos. Thanks a lot. See you when you see me. Bye.
Bye.
Bye. Guys, are we going to have a discussion in the evening? Hello?
Yes, we are.
Because timetable is yet over.
Okay.
The timetable is out. The exam timetable is out.
Yeah.
Yes. Check in the group, my G.
Yeah. Well, yeah.
Hello.
Just a minute, hold on. Let me just stop the video, the recording.
So guys, how are you doing? Thelma, Charlie, Cristobal.